1 minute, please. So already we have started from past 3 days, these 5 essay classes. So first we have discussed what is bioessay, and next I have explained types of bioessay, that is direct, indirect, quantum and quantal. So next, how to measure the types of bioessay also I was discussed. And today I'm going to explain the topic is asymptotic distributions. Okay, 1 minute, I'll share you the topic. That is unit 3. 1 minute, please wait. One minute, I'll wait I will show the topic. So this is I would like to explain the topic. Asymptotic distributions, Feller's theorem, and regression approach to ratio estimate, reference and relationships. So these are we are discuss about the agent, dose, and those relationships only, because it is purely biostatistics. Okay, so we can concern only dose and response and their relationships. So the main objective of this topic is what? First, what are asymptotic distributions and asymptotic distribution of ratio estimator, and one theorem that is in your syllabus, Feller's theorem. Okay, and next, regression approach to estimate dose, response, relation and relationships. Okay, for example, here we can take the sample statistics xn by n such that the limiting distribution of nxn has a finite and non-zero variance, and the transform of xn to make sure that mean does not depend on the sample size. So for example, mean of sample has a limiting variance limiting variance equal to 0, since variance is what? Sigma square by n. Okay, so here multiply n to the power of 1 by 2, variance n to the power of 1 by 2 mean is sigma square. Check mean transformed variable, that is expectation of n to the power of 1 by 2 sample mean equal to n to the power of 1 by 2 mu. The stabilizing transformation is n to the power of 1 by 2 sample mean minus mu. Obtaining an asymptotic distribution for a limiting distribution. Obtain the limiting distribution via stabilizing transformation. Assuming the limiting distribution can be used finite samples. Invert the stabilizing transformation to obtain the asymptotic distribution. For example, n to the power of 1 by 2 sample mean minus mu by sigma tends to normal 0, 1. This is in the statistics. We know that normal distribution, the standard normal variate, its mean is 0 and variance is 1. Assume the limiting distribution works well for finite samples. Then n to the power of 1 by 2 sample mean minus mu by sigma n 0, 1 not. We have placed D for a n to the power of 1 by 2 sample mean minus mu, where n 0 sigma square, sample mean is mu, and then sample mean variance is here, mean is 0, variance is sigma square by n. So n mu sigma square by n asymptotic distribution of sample mean. asymptotic distributions. Other than a few classical results in mathematical statistics, for exact distributional property of a statistics or other random objects is often hand determined to the last details. A good approximation to the exact distribution is very useful. Very use very excuse me, useful in investigating the properties of various statistic procedures. In statistical applications, many distributions say n of them from the same probability model population are often assumed available. Good approximations are possible when the number of repeated observation is large. A theory developed for the situation where the number of observations is large from is asymptotic theory. Why we call the asymptotic theory? Here we can take the samples as small samples and large samples. So large samples is gives us here the as sample increases, the error is minimizes. So that's why we can read the asymptotic theory. Parameters are the unknown values of entire population, such as the mean and standard deviation. Samples can estimate population parameters, but their exact values are usually unknowable. Parameters are also the constant values that appear in probability functions. Parameters are measured characteristics of the population, usually unknown and unknowable at the thing. We are most interested in knowing statistics are measured characteristics of the sample, which we typically use to estimate population parameter that we cannot measure directly. Statistics are the basis for all of statistical inference. Since to infer is to draw conclusions about the population from a sample. Asymptotic is more or less a synonym for when the sample size is large enough. Strictly speaking, you are considering the limit as sample size goes to infinity, but the way people use it is to make approximation based on those limits. Asymptotic distribution of ratio estimators. Mu and nu be two unknown parameters, where here ratio estimated y bar by x bar minus v by mu equal to y bar mu minus x bar by x bar mu. So y bar x bar equal to v by mu, where mu into y bar minus v, where v into x bar minus mu by x bar mu. So this is a simplification. Here we will get n to power of 1 by 2 y bar by x bar minus v by mu is asymptotically normal with mean 0 and variance, where sigma square by mu square plus n2 square n2 v square by n1 v mu to power of 4 sigma 1 square. If x and y are independent and sigma 1 square equal to sigma 2 square, then the asymptotic variance is sigma square by mu square 1 plus n2 by n1 v square by mu square. Check your progress. Space is given below. So these are the questions. Please read. Please, these are very important for your examination. Concept of asymptotic distributions, asymptotic ratio estimators. Say, okay, now coming to Feller's theorem. It is Feller's theorem. So this is most important. This is framed for your subject. So Feller theorem is not applicable in situations where more than one error mean square occurs. Mu and nu be two unknown parameters. Let rho equal to mu by v. P and Q unbiased estimator for mu and nu. This we call, this symbol mu is called, we can read mu. This is nu, N-U-W. We read as nu, it is denoting the symbol is like this. And this is a mu, we can represent mean. Actually, mean is, we know that x bar. But population parameter, we can represent this symbol. Okay, please make note this. And P and Q here, estimators. Actually, we know that P and Q are the probabilities. But here, we are talking P and Q are the estimators of mu and nu. So, assume that the P and Q, the linear in observations that are normally distributed, where R equal to P by Q, be an estimate of rho. The upper and lower confidence limits rho are RL or V equal to or minus G by V2 plus or minus ds by Q. V minus 2 or V2 plus or square V2 minus G in bracket V1 minus V square by V2 whole power of 1 by 2 1 minus G, where G equal to T square S square V by Q square and S square and error mean square having m degrees of freedom. And the estimates of the variance and the covariance of P and Q are V S square V, V11 S square, V22 S square and S square V12 respectively. Also T equal to T m minus 1 n minus 2. So this is a theorem statement. In examination, sometimes they give the theorem and you need to write the theorem. Okay. So that's why please note about the points. Consider P and Q have what they have given estimators of mu and nu. So P equal P rho PQ, where expectation of P rho minus PQ is 0 and has an estimated variance is given by S square in bracket V11 minus 2 rho V12 plus rho square V22 m degrees of freedom. Thus, capital P in bracket P minus PQ rho Q whole square less than or equal to T square S square in bracket V11 minus 2 rho V12 plus rho square V22 equal to 1 minus alpha. The two roots for rho obtained by solving the quadratic in rho within the probability statement will yield RL and R nu the given above. This result will be used in setting confidence limits. The ratio of two means regression coefficients or a horizontal distance between two regression lines, because the latter can be expressed algebraically in terms of the ratio of difference of two means to regression coefficient when Q is large in comparison to a standard error. Then we approximately D equal to 0, then RI RU equal to R plus or minus ds by Q in bracket V11 minus 2 capital R V12 plus R square V22 whole power of 1 by 2. T square S square equal to Q square by V22, G equal to 1. In the quadratic equation 1 by rho, set G equal to 1 and solving the resultant equations obtain R equal to infinity, RL equal to R square V22 minus V11 by 2 into R V22 minus V12. Also, often we will have V12 is 0. 0. The general formula is not valid when G exceeds 1.0. Failure confidence intervals are always wider and those more conservative than the intervals based on Crazy's fiducial distributions. So find the confidence intervals for the natural factor, say, for given data. Normal atrial extract B10 14.6 atrial extract. So here this is the data. The estimate of the common variance is S square equal to 2.749 and pooled sample standard deviation is equal to 1.68. Here we apply Pillard's theorem to set up confidence limits for rho equal to mu by V. Let capital R equal to P by Q. Then the estimates of the variances and the covariances of P and Q respectively. V11 S square equal to V22 S square 2.749 by 0.393 and V12 is 0. If alpha equal to 0.90, then 70 to at the level of significance, the value is 1.78. G equal to 0.11. RU equal to, we will get the value. So here, RU is 0.889, RU 0.889. So RU is 0.091, 0.0861. We assumed that the population variance for the two extracts are the same. So if they are not the same, then one can apply the improvisation of Fellow's theorem obtained by Finney. For example, if variance P rho equal to S square V11, variance Q equal to S square V22, and covariance PQ equal to 0, then one can easily obtain the confidence limits for rho equal to mu by V. RLRU equal to R plus or minus D by Q in bracket S square S1 square V1 plus R square S2 square V2 minus G S1 square V1 whole power 1 by 2 by 1 minus G, where G equal to D square S2 square V22 by Q square, where D equal to D 1 minus alpha 2. So these are only Fellow's theorem. How we can apply the Fellow's theorem, and the proof is given. Please make note, this is maybe an essay question. Next, the regression approach to estimate dose, response, and relationships. Let Z denote dose and U denote the response it induces. Then if U equal to expectation of U, we assume that there exists a functional relation between U and Z given by U equal to H of Z, where H of Z is a single value real function Z for all doses in the range of interest. If that there exists a functional relation between U and Z is given by U equal to H of Z, where H of Z is a single value real function of Z for all doses in the range of interest. If S and T are abbreviations for standard and test preparations, then the regression relationship for two preparations can be denoted U as equal to H of Z, UT equal to H of Z, means S and T. From 3.2, one can obtain the doses Z as ZR that would induce the average response. So here, a minute please. So here, independent Q, that is Z S by Z or is or H or Z, H or S or Z for all Z. So where R is a constant, which is the condition for similarity that is satisfied by all dilution assays. In summary, the average response induced by a standard preparation as a dose response regression function UH by RZ. A test preparation has a dose response regression function UH or Z, where R denotes the potency of the test preparation related to the standard, namely the number of units of effective constituent of the standard preparation equivalent to 1 unit dose of the test preparation. An estimate capital R of R is suggested from observations mode on dose response tests. If the data arising from series test cannot be described by the same form of regression function for both preparations, then either the assumption of similarly is incorrect or the condition of testing have been different or the two preparations. It may happen that over a wide range of responses, two functions are nearly the same, although at extremes that may differ significantly, then the condition of similarity holds a reasonable well. In a comparative dilution assay, its validity need not hold under conditions other than those of its estimation. In an analytical dilution assay, the estimate of potency should be independent of the experimental method and the assay technique employed. Or the questions of these topics. 1 minute. Yes. So this is a black 2. Just I'll give some introduction about this topic. Logit and probit approaches. Logit and probit approaches when dose response curve for standard preparation is unknown. Quantile responses. Methods for estimation of parameters. Estimation of extreme quantiles. Dose allocation scheme. Polycotomous quantile response. Estimation of points on the quantile response function. Logit and probit approaches when dose response curve for standard preparations. Unknown quantile responses. So this is the topic unit 4, and these are, listen carefully. Logit and probit approaches when dose response curve for standard preparations is unknown. The quantile responses. So the main aim of study is logit and probit approaches. And to understand logit and probit approaches, when the dose response curve for standard populations is unknown. Standard populations is unknown means here mean and mu are known. Here mu and mu are unknown. So and quantile responses. The logit and model uses something called the cumulative distribution function of the logistic distribution. The probit model uses something called the cumulative distribution function of the standard normal distribution to define f of. So both functions will take any number and rescale it to fall between 0 and 1. Logit functions by taking the logit of the odds. Logit p equal to logit p by 1 minus p. At the relationship between logit and probit is almost indistinguishable. Logit is pi by root 3x probit. In general, if response versus dose data are not normally distributed, Finney suggests using the logit over probit transformation. Finney is 1952. Experimental methods for binary response variables exist for determination of the dose associated with 50% along the dose response curve or tolerance distribution. If the response of the patient can be observed immediately. Logit approaches when dose response curve for standard preparation is unknown. At least 2 dose levels for the 2 preparations are required for calculating the respective slopes. If the slopes are not significantly different, the pool variance B will be used for both the times. Let K dose levels be used and let X is equal to log and dose for the standard preparation. Y equal to log 10 for the test preparation. Ys plus I, mean response of NS. I units receiving the I dosage of the standard preparation. IR plus 1. E, mean response of I units receiving the ith dose of test preparation. The mean values is denoted by X bar is equal to summation NSI XS by summation NSJ X bar, where NS summation NSY by summation NSJ. And analogs definitions of XOR and Y are whole, where the summations are take over at nk levels, then the quantile two implies are x bar minus y bar equal to, sorry, y bar, y minus y bar equal to b into x minus x bar. Y minus y bar r equal to b into x r minus x bar r. So regression coefficient small b equal to summation n y x minus x bar plus summation n t by t x t minus x bar t by summation ns x bar is xs minus x bar s whole square summation n t I x t I minus x bar whole square, where the potential ratio m equal to x bar s minus x bar plus y bar s minus y bar minus y bar s into b minus 1. This all of you well known. This is called a regression. This is called regression. Estimate simply we learn y minus y bar b into x minus x bar. Okay, 1 minute please. So now, so this is the topics we have where I'm explaining. So, so where regression coefficient b equal to, this is the formula, and the example is that is a example we can discuss here. Consider the following data pertaining to weights gain in pounds by piglets in a fixed duration of time when the standard and test preparation of a certain diet are administered to them. So here, standard preparation, test preparation. Unit 1, Unit 2, Unit 1, Unit 2. So then, that is x bar equal to 0.15, y bar equal to 3.9. Then small a equal to 2.8, Sn equal to 0.320, and small a equal to y bar, where b equal to 4.65, where r equal to potency ratio, this is 1.215, s square equal to 0.826, where s square equal to 4.65 into 0.472. So where s equal to 0.23. Prohibit approach to when the dose response curve for standard preparations is unknown. An estimate of potency based upon individual observations that vary widely is of little use unless supported by some indication of its limits of error. Standard errors of the mean tolerances can be calculated by familiar process, and from these must be derived a measure of precision. Consider first the two um, stochastic structure alone. Writing Z as a typical dose, sum of squares of deviations are used to estimate the variance of Z and Z2, Z1 and Z1 and Z2, and two mean doses for S Z minus Z1 for S Z minus Z2. Both sum squares have n minus 1 degrees of freedom. And the usual practice of pooling the sum of squares so as to obtain single estimate of variance per cat sums. It seems reasonable the logical view is discussed. This involves writing S squared sum of two means dose by size plus size 2 minus 2. Have you two variances? Variance of J1 equal to variance of J2 is squared by size. The square root of the standard error of x bar 1 and x bar 2, the equation can be written as r equal to z bar 2 by z bar 1. This is ratio estimate. A standard error of r can be calculated with the aid of commonly used approximate formula. The coefficient of variation ratio of two independent quantities, coefficient of variation a by b whole square equal to coefficient of variation a whole square plus coefficient of variation b whole square. Coefficient of variance is defined coefficient of variance small a equal to standard error of a by a. Application of above r leads for variance of r equal to s square by z square 1 by n plus r square by n2. N and n1 and n2 are the numbers of subject preparations and are equal to z bar 1 by z bar 2 plus the minus standard error. The result of an essay are summarized by limits between which the unknown to potency is almost certain to be lie, although certainty is unbelievable. Rules of calculation and ensure that the statement has a high probability of being correct. By this, we expect the two systems of inference, those of confidence intervals and of judicial intervals, are in common use in all branches of sciences. Example. This is the example. Preparation, Strophanthus mu, Strophanthus 2 mu 1 by kg, our bane, and these are three types. So these are the total and total mean. So here tolerance of three groups of cats, that is for two tincture of Strophanthus and preparation of ovine, and the experimental procedure was essentially as described by per details. The dose was recorded a quantities per kg body weight of a of cat. Unfortunately, the absolute doses are not known. The tolerances per kg body weight are given this. So now, suppose that tincture 2 to be regarded as a standard preparation, and tincture 1 is to be compared with its test preparation from the mean at the foot of above table, that is estimated to produce some results 19.9 mu, and tincture 2 either being just sufficient on average to kill a cat. So an estimate of potency based upon individual observation that vary widely is of little use unless supported by some indication of as limits of error. Standard error of the mean tolerance can be calculated by familiar process and is from reduced by measure of precision. Consider first two Strophanthus tincture alone, writing jet as a typical dose. Some of squares of deviations are used to estimate variance. Z bar 1, Z bar 2 or 2 means thus tinctures as Z minus Z bar 1 equal to 5.5 whole square plus 15.8 whole square etc. by 7, where S is equal to 75 by and 7. But tincture 2 equal to 68.15. With 12 degrees of freedom, both Z bar 1 and Z bar 2 are means 7 observations and therefore have variances is S square by size. S square by 7 equal to 1.71. The square root of this is the standard error of x bar 1 and x bar 2. The equations can be, we know that ratio estimate x or equal to z bar 2 by z bar 1. A standard error for capital R can be calculated with the aid of commonly used approximate formula for the coefficient of variation of the ratio of two independent quantities. The formula is coefficient of variation a by b whole square equal to coefficient of variation a whole square plus coefficient of variation b whole square, where CV, coefficient of variation, is defined coefficient of a equal to standard error of a by a. So application of above or leads to variance of r equal to coefficient of r equal to variance of z1 plus r square variance of z2 by x bar 2. So variance of r equal to s square by z2 square in bracket 1 by n plus r square by n2, where nt and n1 and n2 are the numbers of subjects for the relations and r equal to z bar 1 by z bar t, z bar s by z bar t plus or minus standard error. Variance of r is 0.0145. What बोलेगा? Okay, that అయిపోతున్నది. The ratio of estimate value 1.18 plus or minus 0.12. Next, quantal responses. And this is the topic. The quantal response in a biological assay is usually based on two possible outcomes. That is, common example of the two possible outcomes is death or survival. However, there are several assays, such as that of some in The coefficient of variation is defined. Next one is quantal response. This I will give briefly. So the two outcomes are survival and death. However, there are three possible outcomes, namely active, moribund, and dead. There is a definite order of these outcomes. Active precedes moribund, when in turn precedes dead. It may be more efficient, those outcomes. Active proceeds to analyze the data with more than two outcomes, than combining the outcomes into categories. An approach to the problem based on the method of maximum likelihood has been given by Atkin and Silve and Ashford and Garland provide a general method of analyzing the data when one uses the numbers, targets, or other monotone transformation. The estimates of the parameters used in general method are obtained by minimizing the appropriate to expressions and have the asymptotic properties of consistency and efficiency. The latter set of authors provide a numerical example involve the postuli insections. Maximal information for bioassay enters in uh, the following conclusions based on empirical studies. It is advisable to utilize global responses such as body weight, organ weight, percentage of blood sugar, or any measure that can be quantitatively expressed rather than planning a quantal assay. Quantal response. Categorizing response into grades like 1, 2, 3, 4 will usually be superior to a purely quantal measurement. The weights used in the probit analysis of control responses illustrate that a graded response provides on the average the above and average about twice the information of a quantal response, also graded response in more useful because the latter can be measured over a wider range than quantal response without running into extremes. Quantal responses based on groups of animals are preferable to a series of single observations at several dose levels. Also, observations derived serially from the same animal may be four to six times as precise as observations made simultaneously upon different animals. If it is impossible to take replicated observation on the same animal, the use of traits are those which extend over a period of time. Some animals may die, or some observations may be results at random from those groups eh, whose eventual number is greater than the smallest. So this method will yield an unbiased and balanced experiment as long animals do not because of treatment effects. So get through this example, please, and calculate mean and sx square s square by n. So please note down this example. I am sharing these notes. So this is the example. Computational advantages of the logarithmic transformation are readily seen by application to the data. The logarithm of the tolerance in this table shown where calculation preparation, Strophanthus 1, Strophanthus 2, or Orbin. So these are the values tolerances of one case and another case of the third case. So these total and these mean this S square x, S square x by n, and ratio Sx in covariance. So this 0.4, this 0.3, this 0.08. So each entry has been resolved by 1.0 to simply the estimate arithmetic. This is equivalent to dividing every dose by 10.0, a change of scale that has no effect on calculation and statements of relative potency. The symbol X is used for log dose in accordance with the convention of essentially in linear relations as equation ZA plus log ZB shows homogeneity of variance is a necessary condition for fundamental validity. The basic hypothesis of a dilution essay fundamental validity, if a proper test of this was needed, Bartlett's test for homogeneity of so this is the F ratio calculated among these values is 1.87. The smallest square is 0.008. So here the symbol M as an observation for cap log R will be used for ratio estimate log potency from equation log ZA plus log rho equal to log Z. Its value for tincture 1 related to tincture 2 is cap lam equal to x bar 2 minus x bar 1. So, moreover, variance is 0.0493 whole square. And the assumption of normal distribution of the log tolerances fiducial limits to M are found exactly by direct application of the distribution, where M t equal to 1.972, M t is equal to 0.0178. Until logarithm of those values are displayed here. Hence, the potency of tubing is estimated as 0.33 ml per with limits at 0.64 per. So, the fiducial range is appreciably narrower than that reported in precision estimation, primarily because of the greater number of degrees of freedom available for calculation of the variance. So these are the questions, please get through, and these only will come in examinations, and read carefully if any doubts and let me know, please. So tomorrow I am going to be discuss is the methods of estimation of parameters, estimation of extreme quantiles. So this tomorrow I will explain. Next class I will explain all this. Unit 5. So if you need doubt, please message me. I'm be here. According to the bottle. So till now, all 4 units I explained. If you get any doubt, please ask me and message me. Mm. So let's please see all these of the topics I have explained. Ratio estimate, asymptotic distributions and asymptotic distributions of ratio estimate. And one example, how to calculate F ratio, quantile assays, and logit approaches when dose response curve for standard preparations is unknown. All these topics are finished. So four blocks are finished. The first topic is also very important, and what is director say how to estimate ratio estimate. Ratio estimate is very important for all these topics. Yeah. So, blocks. Thank you all. So we discuss next topic, next class. Okay, thank you. At Borata, Telegraph.